So good afternoon, ladies and gentlemen. Welcome at the EUPAVE webinar towards low carbon and circular concrete. My name is Luc Rens. I am Managing Director of EUPAVE. I will give a very short introduction to this webinar. First of all, a few practical communications, as you already could see. So we are using the Teams meeting tool, not the live event tool, but the meetings tool, because it allows more interaction during the discussion phase after the presentations. However, it also requires some discipline from all participants. So we ask you during the presentations to mute yourself and also to switch off the camera. We also want to inform you that the webinar will be recorded for later use. So let me first briefly introduce our association, EUPAVE. We were created in 2007 as the European Concrete Paving Association, and we want to represent and defend the sector of cement and concrete in European transport infrastructure by work of advocacy, engagement with EU, national and local decision makers, by sharing technical know-how, by communicating all the benefits, promoting innovation and best practices in our sector of concrete roads, safety barriers, and all other types of applications in transport sector, as you can see listed here on this slide. We have members, full members and associate members, we have partners, and you see it goes from large cement holdings, from international and national cement and concrete associations to equipment manufacturers and contractors, and even small businesses, designers, consultants. So all ranges of companies are represented in EUPAVE. The work we do is summarized here by showing our 6 working groups. Best practices working group, exchange of know-how. Environmental strategy, talk about the environmental benefits of concrete. The advocacy working group, mostly at the EU level. Concrete safety barriers. Statistics and communication tools. So everyone who is interested in supporting the concrete pavement sector or in getting support, helping to develop and build concrete pavements, they're always welcome to join us as a member or a partner. Let's come now to the agenda of today. We have a webinar with a title, Towards a Low Carbon and Circular Concrete. It was an initiative of our working group on best practices. However, you understand immediately that it is very closely related also to our working groups of environmental strategy and also advocacy, because the themes that we will be discussing are really the themes of the European Green Deal. First of all, the CO2 reduction or carbon neutrality. As most of you know, all national cement associations, all international cement holdings, they are developing pathways to 2030 to 2050 carbon neutrality. So it is a very topical theme now. But also the circular economy, so the use of the recycled aggregates and other recycled materials is also very important. The circularity is also part of the Green Deal. So we have today 2 presentations. We have 2 speakers. I present to you our first speaker, which is Edwin Vermeulen, who is the Secretary of Director of the Cement&Beton Centrum at the Betonhuis or Concrete House in the Netherlands. Edwin is a materials engineer. He's specialized in concrete, mortar, cement, and mixtures and aggregates, and he has a research focus on the use of alternative and secondary binders, fillers, and aggregates. So I think he is the ideal person for this first lecture on CO2 reduction options for cement. So, Edwin,
It seems Luc is leaving the meeting, but nevertheless, I thank Luc for the introduction, and I will start sharing my presentation. Yes, I'm going to talk about options for cement for CO2 reduction, because cement is the responsible for 80% or over 80% of the CO2 profile of unreinforced concrete. And of course, if we want to reach net zero carbon in 2050, also we need to address concrete itself and of course design of buildings, etc. But of course, cement plays a very important part in this. I'm going to try to explain why it's so difficult to find alternatives for Portland cement clinker. Portland cement clinker is the main component of cement. But to do this, I have to start with the raw materials and with a bit of history of the development of Portland cement clinker. I think that's really necessary to understand the research on alternative binders. And of course, in the second part, I will discuss alternatives, but also carbon capture and what we can do now to reduce the CO2 profile on the short term. Here you see the world production of materials. The largest amount is cementitious material, which is of course mainly concrete, but also mortar and plaster and so on. But as you can see here, compared to other materials, it's really a lot. We produce more concrete than all other materials combined. So if we are going to look to alternative materials, alternatives for cement or for concrete, we have to keep this in mind. We need really a lot of material. Here you see also a lot of wood, but here wood is for over 50%, of course, in the form of paper and furniture, and only for a small amount the use of building material. Now, of course, if you're going to look at alternatives for cement and concrete, then we have to look at the CO2 profile of alternatives. Here you have a picture of different materials, including asphalt. And here you see that cement has quite a high CO2 profile compared to other materials, but of course cement is only used for a few hundred kilograms in a cubic meter of concrete. And if you look at concrete, then it has actually quite a low CO2 profile compared to alternative materials, also compared to cross-laminated timber. Asphalt is a little bit has a little bit lower CO2 profile than concrete, but of course, if you compare it on the lifespan of a concrete road of 40 years or more, then of course concrete is more environmental friendly, not even taking the albedo effect and other aspects into account. Of course, we always heard that concrete is responsible for 7 or 8% of the man-made CO2 emissions worldwide. But that is clearly not due to the CO2 profile of concrete, but it has all to do with this enormous volume of concrete we produce. Here you see a reason why we produce a lot of concrete. Here you see, I'm going to try to start my pointer, but yeah. Here you see the increase in world population to above 7 billion people. And here you see the increase in cement, which started around 1975 to increase strongly, and especially after 2000. That was mainly in China, but also in other countries, due to the increase in prosperity. Once a society develops, people want to shift from wooden to concrete buildings, and need to have infrastructure, sewers, and things like that. So that explains, of course, the strong increase in demand for concrete. For concrete we need a lot of material. Cement is mainly produced from limestone and a bit of clay, but mainly limestone. And here you see what we need of limestone every year. It's more than a cubic kilometer of limestone we need, and you see the Eiffel Tower next to it, and this is on scale. So if we search for alternatives for cement, it's clear we need a lot of alternative material as well. And for concrete, of course, we need 6 times as much as this for the aggregates. So alternatives have to be abundantly available to take, to consider them. Now, of course, then we cannot use critical raw materials. Critical raw materials are not necessarily scarce, but if they're not scarce, they're only available in a few countries. This was actually the main reason behind the circularity in Europe. In Europe, we noticed that we were, for a lot of materials, dependent on countries like China. And that was the main reason to start focusing on recycling on those critical materials. And interesting is here, for example, this phosphate rock. You can make a binder from magnesium phosphate, and it's actually already used for specific applications like repairs. But as you can see here, it's a critical material that we need it also for our agriculture, for the fertilizers. So if we start using this for to replace cement, then of course we will run into problems very soon. And so these type of materials are not available for replacing cement. Now that's also of course the case for scarce materials. Here you see a list of scarce materials, moderately scarce and not scarce. And what's clear that calcium and silicium, the main components for use for cement and concrete, are not mentioned. They are basically unlimited available. Here you see also aluminium. Aluminium is not mentioned as scarce, for 20,000 years available, but that's based on the current production of aluminium and a growth assumption of 3%. But if we start using aluminium as a raw material for cement production, and we will discuss that later on for one type of alternative binder, then this 20,000 years, of course, will be strongly reduced. So that's important to take into account. Also for iron, iron is moderately scarce, 300 years available. But we need iron for cement production. But here we use clay. We need iron only in a very small amount, and it's sufficiently available normally in regular clay. And that's also the case for aluminium. We also need aluminium, but in small quantities available in clay. And clay itself is also, like limestone, abundantly available. Like I said, raw materials for cement are unlimited and regional available. And it's interesting to mention that limestone is produced every year in larger quantities than we use for the production of cement. Limestone is basically skeletons of plankton, and in the oceans you will every year about 5 billion tons is produced, which is more than we need for limestone production. Of course, we cannot use this in LCAs because it is in the same time scale, but not on the same place. But nevertheless, if we are able as a society to quit using fossil fuels, then the CO2 in the atmosphere would go down despite calcining limestone. Now I would like to switch over to a bit of history. Of course, people like to live in stone houses. Of course, we started in tents and in caves and probably also in wooden buildings, but soon moved to adobe, which is dried clay, sun-dried clay. That started around 8000 BC, and it's still in use in Africa and in Southern America. You will see buildings still built in adobe, and it is also very environmental friendly, labor intensive, but environmental friendly. Yeah, but of course not really an alternative for concrete. Those buildings last only a few decades, need much maintenance. They are not very resistant to rain, so especially not suitable in our environment, and not very strong. You cannot go higher than what you see here. Then around 4000 before Christ, lime was invented, probably by the Egyptians, but you will also find other possibilities. But this was, of course, a huge step forward. And lime itself is quite circular product, as you can see here. You produce, you start with limestone, it's found in nature. You burn it at 1000 degrees. Then you get burnt lime, and you combine it with water. And then the slaked lime you can use to make a mortar with sand and start building, or coat the adobe, as also happened. So this was quite a step forward. But of course, it also has a disadvantage. It takes a lot of time to harden, and it's of course not as strong as pure Portland cement. If you start building walls with lime, they have to be really thick. Because the C2 has to ingress in this mortar, it really takes a lot of time. The Romans improved this lime by adding a pozzolan. This pozzolan that could be ash of volcans found in the neighborhood in Pozzolana around Vesuvius. But they also could use ground tiles as a pozzolan, and this pozzolan that takes the lime from the lime, the burnt lime, and can react with it and form CSH gel. That's the main component in also modern cement stone. The next step was hydraulic lime. You see here an old building. This is the Hagia Sophia building around 500 AD. But if you look closely at the mortar, then you will not only find limestone, hardened limestone, but you will also find CSH gel. So this was actually more or less already an hydraulic lime, or a combination of regular lime, pure lime, I must say, and a pozzolan. Hydraulic lime was actually invented after 1800. It is lime but combined with clay, or in the past it was probably, you can say, dirty lime. But if you combine it with clay, then you get a first component we have in modern cement. Now here you can find actually the figure of producing modern Portland cement, but you also will find the steps in the past. Here you have the limestone, and in modern cement here we have a part of clay. But of course this happened in the past, producing lime mortars. And later on with the hydraulic lime, when clay was added and a higher burning temperature, we were able to produce this component, the C2S, the belite. And in modern Portland cement, we go a bit higher in temperature, and we are able to produce the main component of modern Portland cement, and that is C3S, the allied. So here you see a composition of modern Portland cement. We mainly have the C3S, a little bit of the C2S, the baelite, and those components with aluminium and iron we actually don't need, but they help to keep the burning temperature a bit low, and those are coming from the clay. Here we have the roadmap for CO2 reduction. Here you see that a large part has to come from carbon capture and storage or carbon capture and usage. And only a small part is expected to come from alternative clinker. Here you see that we expect to get 117 kilograms CO2 per ton reduction from clinker substitution, or sorry, from cement itself, but of which 72 of clinker substitution. And that includes these alternative binders, but also replacement by slag and fly ash, limestone and burnt clay and other alternatives. So it is already explained that it will be difficult to find alternatives for regular Portland cement clinker. Now the simple step is to substitute clinker by alternatives. That's already being done on a large scale. Here, for example, if we have slag, most of the slag produced worldwide as a byproduct of the production of pig iron is already used as a component in cement or directly in concrete. Fly ash is not fully used because they are not all suitable, but of course fly ash will be phased out because we're going to end with the coal power plants. But what we can have in the future as well is, of course, filler. This is limestone. We can produce that without any limit, and we can calcine clay, and then we have, of course, also a limited availability of clay. And that's not currently done because we still have sufficient slag available, although only about 8% of the total cement production. But you will see that in the future more and more calcined clay will be used to reduce the clinker content in cement. Now, if we're going to look at alternatives for Portland cement clinker, like I said before, we have to look at the availability of the raw materials. We cannot use, for example, this phosphor due to the fact that it's insufficiently available. Here you see the composition of the Earth's crust. Of course, this is oxygen, silicium, aluminium, iron, calcium, sodium, potassium, and magnesium. And if you look at modern cement, then all those components are already in. We don't need those two, but they are inevitable. They are so abundantly available. They are also, of course, in the raw materials for the cement production, but we need those components. And if you look for an alternative, you should look at those elements to find an alternative to make sure that they are available. But that's not the only restriction. Of course, it must also be chemically possible. Cement particles have to be able to dissolve in water. The reaction products must have a larger volume than where you started with, otherwise you won't build up any strength. And the resulting products must be poorly soluble in water. And if you look at those restrictions, so both the availability of materials and the chemical possibilities, then you end up with the three products I've mentioned here, the calcium silicates, the calcium aluminates, and the calcium sulfoaluminates. That's basically what we have as possibilities. Of course, I say here hydraulic cements, that means reaction with water. The alternative reaction is a reaction with CO2, and that's one of the examples I will come back on later on. This is the first alternative, baelite-rich Portland cement. This is a little bit back to the hydraulic limestone I mentioned earlier, although not using limestone calcium hydroxide, but mainly using baelite. Here you see it. the high baelite cement has a relatively large amount of this baelite and a relatively low amount of alite, the quickly reacting component of regular Portland cement clinker. And this is a comparison with Portland cement. A bit of a strange Portland cement. Normally this amount is higher than what's here the reference. But the reduction is only 10% in CO2 emissions, and we have a very slow strength development. So it's only suitable for very specific applications like this 3/4 dam where it was used. There you have the advantage of a very low heat development. Now, a more serious alternative is the baelite calcium sulfur illuminate cement. That's also baelite, but then the reaction is speed up. The slow reaction of this baelite is speed up by adding yeelimite, which is a combination of calcium, aluminium, and sulfate. And this forms ettringite, and that helps to speed up the hydration of the baelite. There are, I must say, several types of this cement under development. So most large cement producers have their own type, and they all differ a little bit. But they all need aluminium as a source. Sometimes, depending on the type of product, a secondary material can be used, like fly ash. But often you need this pure bauxite as raw material, and that is expensive. And if you want to replace the whole volume of Portland cement, of course, you will run out of this bauxite in the longer term. But interesting, in principle, it can replace Portland cement clinker. But the downturn, the pH is a little bit low with 10.5. So it will be more sensitive for carbonation, which is of course a risk for reinforced concrete. And due to the low pH, it is a bit more difficult to activate replacements of clinker like blast furnace slag and fly ash and calcined clay in the future. So that's, you have to use it more or less in pure form, and then you have this 25% reduction compared to Portland cement. Solidia cement is another interesting alternative. It's a product of LafargeHolcim. It's basically wollastonite. Wollastonite is calcium silicate, so CS instead of the C3S, and it has to react with CO2. That limits the sizes of the products, so you cannot process it like regular concrete. You have to produce relatively small products and then store them for 24 hours in a CO2 chamber in order to let it react. But then you have a very quick strength development, so it is interesting, especially for unreinforced applications. So it reacts with CO2 instead of water. And interesting, you use the same raw materials and the same furnace as we have now. So it should be relatively easy to produce this product, but a bit difficult to process it into concrete. But the CO2 savings are quite high. You have 30% during production, mainly because you use much less calcium, much less calcium than with regular Portland cement, but you also have the CO2 absorption during the hardening, so that makes it really interesting. Now here you have this process. You have here you cement grain, the wollastonite, water as a medium, and then the CO2. And here you have the reaction product, and here you can say the microstructure of Solidia cement, remains of the cement grain, silica gel, embedded in calcium carbonate. Now another interesting alternative is Litement, which is a product. I must say, shrink is the industrial part of Solidia. It's still in the laboratory phase, but an interesting development. This picture looks a little bit complicated without any chemical background, but the main thing is that here you produce Portland cement with 3 parts of limestone, calcium carbonate, the green is the CO2, which is released when burning the limestone. And if you produce the cement, you only use 1 part of calcium carbonate, so you have much less CO2 in the air. But the process of this cement is quite complicated. You need an autoclave, and then you have to grind it again. Now that looks simple, but in practice this is a complicated process to get it stable and to make it on a large scale. The end products are of course also different. We have the CSH gel after reaction with water, that's in both cases, but with pure Portland cement you get 2 of those calcium hydroxide units which you need for the high pH, and here with cement you don't have those calcium hydroxide, so you end up with a low pH. You can process it like regular cement in concrete, so that's really an advantage compared with Solidia. But the low pH and the complexity of the process, that makes it difficult. Here is the summation of what is said. Most of it is, I think, lower temperature, same raw materials. That's important, but a complex production process. But you can process it like regular cement. And CO2 savings are high, 50% to compare to Portland cement. Then we have the geopolymers. Clearly you can build with geopolymers like you see in this example, although the examples are still limited. If you go to a webinar about geopolymers, you have about 50% chance you're going to see this picture. And if you ask then the lecturer, have you been there yourself, then the answer is mostly no. So they didn't check. Me neither. I haven't been there, but I checked on Google Maps. It's still there. I don't know whether this is scaling or not. Maybe not. Maybe it's a coating that has been lost. But clearly, you can build with geopolymers. But whether it's suitable for road construction, that remains to be seen. Here you have 2 examples of geopolymers used recently in bicycle paths, cycle paths in the Netherlands. After only 1 week of snow and frost, they were heavily damaged by scaling. I would say much more than you will find with regular Portland cement based cycle paths. I must say there are also good examples, for example, a roundabout in the Netherlands from geopolymers, which is still looking very fine after 3 years. But I would say more than 50% is substantially damaged. Probably because it's not really a geopolymer with cross-linking between silicium and oxygen atoms, but it's mainly alkali activated slag, and then you still have a calcium silicium hydride, so CSH gel, but without a calcium buffer. And so I expect that the carbonation causes this this damage. The carbonation, like with blast furnace slag cement with a high slag content, results in the formation of a porous silica gel. So geopolymers already used in the 1950s. But important, if you use slag and fly ash, they are already used in concrete or in cement, then you don't have any environmental benefit, but only a replacement of the use. And actually you have an environmental loss because you have the additional activators you have to use with a high CO2 profile. So if you want to have an environmental benefit, you need additional sources of materials that are not currently used in concrete, like calcined clay or perhaps fly ashes that are not suitable for regular concrete. Carbon capture. I explained how difficult it is to develop alternative binders based on availability and based on the chemistry. So that's why we also need carbon capture to reduce the CO2 profile of concrete and to reach net zero in 2050. Now, the main idea about carbon capture is, of course, to concentrate the CO2 in the process. Otherwise, it would be way too expensive. And here are a few examples how to do that. Oxyfuel, for example, is not using regular air in the kiln, but using pure oxygen in the right amount, sufficiently to burn the fuel. So you will end up with a very high CO2 concentration at the end of the kiln. And the left system is a separate calcination of the limestone, so you will have pure CO2 from the limestone. Of course, in that case, you are going to miss the CO2 that's released by the burning of the fuels, but this is in any case for about 60%. It will capture the CO2. And the third picture is using an amine solution to capture CO2. You can capture the CO2 from the gases in this amine solution, and then you can release the CO2 again by heating it up to 120 degrees, and then you will end up with pure CO2. And this type of carbon capture is going to be installed on a large scale in a factory in Norway. So these are only 3 examples. There are more examples. You can do the same as with amine solution with lime itself by capturing CO2 around 600 degrees with calcium oxide and then heating it up to 1000 degrees and keep up looping the calcium to capturing and releasing the CO2. Then of course, what are you going to do with the CO2? Well, there is sufficient capacity for storage in nearby empty gas fields for hundreds of years, actually, not only for the cement industry, but for all large emitters. But of course, we want to end up with the use of CO2 to produce ethanol or polymers or algae, that's already tried, but also to activate recycled hardened concrete. If you use the smart crusher, you will end up with cement stone, and if you grind it and activate it with CO2, you will have a product, more or less a puzzle, and you can use again as a main component in cement. So conclusions, if you look at the earth crust composition and chemistry, then yeah, it leads to Portland cement. So it was not by chance that we ended up with Portland cement, and there is one alternative that can replace Portland cement clinker in terms of availability and quality. So we need a lot of different measures to reach a significant CO2 reduction. And in my view, this calcium sulfur-aluminate belite cement, the solidus cement, but especially carbon capture are promising to help in this net CO2 target. But we need time, that's for sure, especially for carbon capture, despite already one plant being on a large scale adapted. It will need 10 years or more before we will see it on a larger scale. So that's unfortunately on a short-term availabilities to reduce CO2 are limited. But what we can do is, of course, use low clinker cements as far as possible. But of course, don't go too low with your clinker content because we need the frost resistance for our roads. Optimize grain packing. I really think that can save, if you do it very well, 20 to 30 kilograms of cement per cubic meter or even more. Use alternatives as far as available. For example, carpstone, although of course the volumes of those alternatives are limited. Yeah, and use coarser gravel whenever possible. The coarser the gravel, the less cement you need. That's the end of my presentation. I will end sharing. Are there any questions?
So thank you, Edwin, for this clear presentation. Clear, however, sometimes a difficult chemistry course. So indeed, the floor is open for questions. And so you can raise your hand, and I see already one hand raised from Viva Kunik. So you can switch on your camera and your microphone and ask the question. Then afterwards, Edwin will try to reply.
Yeah, thank you very much. Nice presentation. You hear my voice?
Yes, sure. Yeah.
Yeah. Well, I was wondering the fibers, either polymer or steel fibers used in the concrete pavements. We have used them in Turkey in few locations, but it seems that even they have high tensile strength. I'm sorry, just a second. Even we use them in reinforcement with the concrete pavements, we did not have such successes. We were expecting high tensile strengths. Rather, we didn't see much in the tensile strength. And we're trying to solve the problem because the fibers have 500 megapascal tensile strength, whereas when we apply the loads, it doesn't really have effects on the either on the compressive or on the tensile strength. And we noticed that after looking at the microscopic level images, we found that the bond between the cement is not that much good. Did you have similar experience, and what are the solutions?
I'm not an expert on steel fibers, but if you use steel fibers, you will not notice an influence on normally with normal steel fibers on strength, not on the compressive strength and not on the tensile strength. That's not the case for the very small steel fibers we use in ultra high strength concrete, but in regular concrete with, let's say, only 30 kilograms of steel fibers of a length of 30 centimeters, 3 centimeters, 30 millimeters, they will not influence strength of the concrete itself. Of course, they will only start working after the concrete has cracked. And then, of course, if you use the 3 or 4 point bending tensile strength, then you will see that they will have a positive influence. But in practice, the results are, in my view, a bit disappointing. You really need a lot of fibers to be effective. Of course, they are all over your concrete. So also, let's say, the majority of the fibers are not on the position where they help.
Yeah, so you agree with my conclusion that there are lots of work needed to be completed in the subject matter, and I still consider fibers as a positive impact on future performance of the concrete pavements, because the steel in Turkey has tripled over the 3 years. It's not just because the dollars increased or the gold increased, but rather there is a lobby, like asphalt lobbies and other lobbies are intentionally increasing the prices. But the fibers are their costs are reasonable. They have been used in the tunnels, but on the concrete pavements, I think if the other audience agree, there are lots of studies needed to be studied on the side. Thank you very much.
Yes, well, we do have some experience. You can always send an email to info@eupave.eu and we can give some further comments on that. But I see that another hand is raised by her colleague Thierry Cedron from Eiffel University from France. Thierry, go ahead.
Thank you, Luke. Thank you for the presentation. I didn't catch why you say that the geopolymers are not interesting on your slide 28. You say that it's not interesting because we use slag and fly ash that are already used in composed cement.
Yeah.
But you don't have in such a product, you don't have the part of clinkerization. So. Which is the main producer of CO2 in the cement
But
factory.
If you compare 1 cubic meter of geopolymer based on slag and 1 cubic meter of regular Portland cement, of course your environmental profile of that cubic meter of concrete is better. But you have to look at a larger scale. Slag and fly ash are already fully used in concrete everywhere in the world. So if you produce geopolymer on those, based on those materials, you only get a replacement. So that, for example, if you use all slag in geopolymers instead of blast furnace slag cement, then the users of this blast furnace slag cement will have to switch to pure Portland cement. That's
okay.
You
catch it. Okay. Thank you.
Yep, you're welcome.
Yes, indeed. So availability seems to be a key word, and also where to set the boundaries of the system that you are studying. In this case, for CO2 reduction, it's a global problem. Are there any further questions? Yes, Manu, you can ask your question. Go ahead. Mr. Diependalen. Manu, please unmute yourself and you can ask your question. No, he lowered his hand. All right. Okay, if there are still questions, you still can ask your question and we will still can give a reply afterwards after the second presentation. So I take the oh yes, there is one. We take one more from Tim Groeneveld.
Hi, thank you for your presentation, Edwin. I also had a question, and maybe it's a bit broader question, a bit zoomed out. But what are the challenges in implementing those new technologies? What is needed for the building sector and the infra sector to take over these new technologies and implement them?
That's a difficult question to answer because they differ from topic to topic. If we're talking about the development of alternative binders, we need, of course, facilitation of trials of those materials. But for example, in the Netherlands, we have fortunately opportunities from Rijkswaterstaat. They are experimenting with new types of concrete and new types of binders, for example, in the afsluitdijk. And really need that type of trials, large-scale trials, to test them in practice. Yeah.
Thank you very much.
Yep, you're welcome.
Okay, so now we'll continue with the second presenter, and that is Mr. Bram Dooms. Bram is civil engineering construction from the Free University of Brussels. Bram is assistant head of the laboratory of concrete technology of the Belgian Building and Research Institute. First, he was a researcher, and now he's assistant head of laboratory. His most recent project was about a circular concrete, and that is precisely what he is going to present now for us. So, Bram, go ahead.
Thank you, Luc. Can you hear me? Everything's fine?
Yes, it's fine.
Okay. So we just got a story about cement and how we can improve the environmental impacts of cement. in concrete, and now I'm going to try to do the same thing with the aggregates in concrete. First, a little context. So in the concrete production, we use a lot of materials. Cement is one of them, of course, but a large portion, about 3/4 of the volume, is taken in by inert material, the aggregates. And so you saw the quantities of material of concrete produced every year in the presentation of Edwin. I'm going to come back to that also, but it's just an enormous volume. And particularly about the sand, we begin to see messages in the news about a sand shortage. Of course, there is a lot of sand in the world, but not all sand is can be used in concrete production, of course. So this is a graph about the CO2 emissions of the cement industry. So you have a shortage of materials. You have the CO2 production of cement, and together with the aggregates and the transportation, this goes up even more than 5%. So we get to 8% of the total CO2 emission related to concrete production. At the same time, there is a lot of debris that comes out of buildings, pavements, also roads, and a lot of the debris is already used, but it's rather low quality applications, and this leads to sometimes alarming messages in the news, like this one: concrete, the most destructive material on Earth. Of course, you have to see this in perspective. It's only destructive because such enormous volumes are produced every year. To lower the environmental impact of concrete, a lot of developments already have occurred. A lot of firms are already beginning to innovate and to search for alternatives for the cement, of course, for the binders in the concrete, but also for the recycled, for the aggregates, the natural aggregates. And so we also, as a BBRI, we conducted a lot of research projects to improve the application, the use of the recycled aggregates, and to show that you can go further than we already are allowed to. But of course, there are a lot of innovations. We can see them. The companies come to us. They develop some things, and they are sure they can use their materials into concrete. But we have to acknowledge that a lot of those innovations don't make their way into practice. So there is some kind of void between the researchers and the contractors, the designers that design buildings and structures, and so not all of those innovations find their applications into practical cases. So this, why is this? On the one hand, a lot of times the argument is raised that in fact the technical framework to apply these innovations is not complete. It's too difficult, too complex to follow all the rules that are already in place. And on the other hand, it's unknown territory, and the construction industry by nature is very traditional. We have the rules, we have the way, our way to work, and it's very difficult to do something else when something we know is already good, not taking into account the environmental impact, of course. So because of this, additional innovations also have difficult to develop further, because when there is no ground for application, why should they investigate further and innovate? So there is some difficulties to get these new technologies, innovations into practice, and that's why we at BBRI started a project in 2018 named Circular Concrete. It's a project that is funded by Flanders on the one hand, and on the other hand by 27 companies, innovators that produce, that develop their products, and they want, in fact, to see their product into practical cases. So what we did is we did a state-of-the-art review, a SWOT analysis of different technologies that are available that improve the circularity of concrete. Some of these technologies we investigated further on a lab scale to see how far can we go, how interesting are these innovations really for Belgium anyway. Then with BBRI, we supported some test cases. We did some research in lab. We talked to different parties to get the technologies really into practice. And we also did an evaluation of the environmental impact of different solutions, which is not very easy to do because you have to take into account a lot of things in the LCA analysis. And we put all the results into different reports. So there is a lot of knowledge. There are cases that were followed. We drafted a practical guide to put innovations into practice, and we also did some events to present these findings. If you are interested in the results, you can go to the website circularconcrete.be. Of course, it's the project that was funded by Flanders, so a lot of the reports are only available at the moment in Dutch. We're going to translate them also into French, and it will be available on the website in a few months. In the project, we started with the state-of-the-art, and we looked at different aspects of concrete. For example, the primary resources, aggregates, cement. Cement I'm not going to tackle in this presentation because Edwin also already gave a very complete presentation of that. But we can also look at the design, the mix design, the construction process to improve, the recycling process, the reuse, demolition of concrete structures. There are innovations that look at that, and then of course there is also the valorization of secondary materials, slags, recycled aggregates to be used into concrete. So in the state-of-the-art, which is also available on the website in Dutch at the moment, we looked at the different technologies available at the moment regarding concrete composition. So the binders I'm not going to tackle today. I'm going to talk about the aggregates. The design and building process we also tackled in the report, and different innovations were discussed, but I'm not going into it here. And then also the use during the use phase, you just prevent that constructions are being demolished. So largen the lifespan of structures it falls into that category, and also end of life. So how can we improve the recycled aggregates coming from the demolition of concrete structures? How can we improve the use of these materials? So when we look at the concrete composition and the aggregates, around 70 to 75% of the volume is taken in by the inert materials. So we have the fine aggregates, the sand, and we have the coarse aggregates. And then there is the binder, the water, some air, some secondary cementitious materials, and then mixtures. But you can see that of that enormous volume of concrete that is produced, 3/4 are coming from aggregates from inert materials. And here we can see how many tons of aggregates we need to approximately, of course, we need to build the structures we are used to use in all day life. You can see here 30,000 tons aggregates necessary to build 1 kilometer of roads, a nuclear plant, 12 million tons of aggregates needed to produce all the concrete that is needed here. So enormous volumes. All of these aggregates, they have to be mined somewhere. They have to be quarried, mostly from the quarries, of course. You can also get the aggregates from riverbeds and from the sea, but those from the riverbeds, those aggregates are being more and more depleted. So there we cannot use the quantities that we need for concrete anymore. And the aggregates coming from the sea, the coarse aggregates, they are not really, they cannot be used as such into concrete. They are not of high enough quality. The form is not good for concrete. So we're mainly looking at the quarries for the coarse aggregates. And so all these aggregates have to be quarried, they have to be treated, washed, broken, and then transported to the concrete plants for the concrete production. So that's a lot of activity to produce those aggregates. Now we can improve the impact, of course, by replacing some of these natural sources, natural materials by materials that we get from the construction debris. That way, when we reuse them locally, we win in the quantity of aggregates that need to be quarried, and we also limit the quantity of debris that has to be put elsewhere. So there we, out of this debris, we can get recycled concrete aggregates and recycled mixed aggregates. The gains there is, like I said, less consumption of natural resources and less transportation. Of course, we cannot put them into concrete as such without taking into account anything. We have to look at the water management, which is very important. When we look at concrete, recycled concrete aggregates, schematically here on the right, you can see one of those aggregates. In fact, it is composed of the original rock aggregates in the primary concrete, which is, and it is surrounded by cement paste. So instead of the original rock aggregate, you get a material that is composed of the original rock aggregates and a mortar. Oh, I'm just a minute. Yeah. So of course, this recycled concrete aggregate is going to absorb more water. The cement paste is porous, more porous than the original rock aggregate, so it's going to absorb a lot of water. So in the concrete mix, you have to take into account the high water absorption of these aggregates. So you have to add a little more water to the mix, but you have to make sure that this water is absorbed and does not remain in the cement paste, because it's going to lead to a higher water to cement ratio and less quality concrete. Another thing to look at is the continuity and the purity of these materials. Of course, this is not a continuous source of material. This comes from the debris, from roads, from buildings, so the quality is not constant. And so you have to make sure that when you make concrete with these materials, that the quality is uniform, and so the quality of the concrete is under control. Of course, when you look at the schematic of such an aggregate, you can see that this will have an effect on the strength properties of the concrete and also the durability properties of the concrete, because these aggregates are more porous and will allow the ingress of CO2, of water, of other substances more easily than the original rock aggregates. So these are the consequences when you want to use these materials. On the other hand, we can also look at the manufactured aggregates. We're looking at industrial byproducts on the one hand, mainly the slags coming from metallurgic industry, and you know, the impurities in the production of the steel and of the metals. They are extracted and grounded, so they can be used in the cement production, for example. But you can also look at them as an inert material when you use them in coarse condition. You can also look at the waste streams from other industries, ashes coming from incinerations plants, polluted soil that is being washed and cleaned and can be reused into concrete as an inert material. The gains there is like the recycled aggregates, less consumption of the natural resources, less transportation when we work locally and we treat these aggregates locally. And of course also less waste, because these products are more, especially the waste streams, are dumped otherwise and used in a very low quality setting. The attentions with these products when we're using them in concrete is also the continuity and the purity of these materials. You can consider that ashes coming from incinerations ovens, they will not be very continuous or the composition depends on the primary product that you're incinerating, and the same thing with the polluted soil. So it can be very variable in composition. Also, the chemical reactions. Sometimes these waste streams and slags they contain certain elements that can in alkaline environments with water, they can react chemically and rise in volume, for example, or cause other reactions that are not very good for concrete. And then there is also, of course, the second and third life, the leaching of these materials. We're talking about slags, metals, incineration, waste streams that contain some pollutions or heavy metals sometimes. And they can be okay when we use them in concrete, but afterwards, when the concrete is broken into small parts and put somewhere else, at that time perhaps it can leach anyway to the soil and cause pollution. So those are the main attention points when we're going to use these aggregates into concrete. Now, the current standard for concrete, I'm not going to talk about road concrete, because I'm not specialized in that, and I know that the design rules and the application rules are slightly different than the ones for cast in place concrete as described in the standard EN 206. But in the EN 206, the standard allows already to use recycled and manufactured aggregates, but it says in fact that it's only recommendations, so it's not normative, it's only informative. And in fact it says that you can use them, but the suitability has to be established by the provisions valid in the place of use. In fact, the standard says you can use them, but in fact the national annexes of the 206 have to individually allow or describe what is possible to do with these aggregates. When we're going to look to the Annex E in the EN 206, it's an informative annex that describes how to use regular aggregates, but also the recycled aggregates. And there we can see that there are, in fact, some rules for the aggregates themselves to be used. Type A is then the concrete recycled aggregates, and type B is the mixed aggregates. So there are some demands regarding the composition of these aggregates. And then there is also the percentage in which we can replace the natural coarse aggregates. And you can see we also speak only about the coarse aggregates. The standards they don't speak about the fine aggregates, the sand in the concrete. Now, I can only speak for Belgium, of course, because other countries I'm not specialized into it. But the Belgian standards since 2018, in the normative part of the standard, so it's not an informative or recommendation, it's very normative. They say that in fact the general suitability is established for the recycled concrete aggregates. You can see here a plus in the European standard. It only spoke about A. So in Belgium we go a bit further than the requirements for the A aggregates, mainly for the oven-dried particle density and the Los Angeles coefficient. So the general suitability is established, but we cannot put these aggregates in how we want in the concrete. It is limited to strength class C30, 37, and also the replacement percentage of the coarse aggregates is limited to some very limited presentations. So in fact you can use them, but the application is still very limited. But so there are already concrete plants that that can deliver the concrete following very with respect to the standard with recycled aggregates. Also for the B aggregates, you know, the mixed aggregates, the concrete already gives guidelines of how to use them into concrete. So you can already use them, and the same is true for manufactured aggregates, but it is very limited regarding the composition. You cannot put whichever slag into the concrete. It's limited to certain types. Also, the fractions are limited, and also the producers, in fact, have to still provide the proof of suitability in concrete that the aggregates have no negative influence on the properties of the concrete, and it is also limited in class, in strength class, and in the application. You can only go to up to XC1, which is very limited field of application of these aggregates. So, but it's already possible to do this. However, of course, it only becomes interesting to use on an environmental field if you can go higher than what the standard is already allowing. So you can do that. The standard says that, in fact, if you want to go higher in replacement percentages, higher in the application, so the strength classes and the exposure classes, when you want to use other fractions or other types of manufactured aggregates, you can do it, but you have to establish the general and or specific suitability. For some of the aggregates already described in the standard, the general suitability does not have to be established, but only the specific suitability. And with the general suitability, in fact, it's just you have to show that you have your product under control. So the properties they remain within certain fixed limits, and also that the concrete can be used with a predictive behavior into concrete and no side effects for the concrete or rebars. So that is the general suitability that has to be established for the aggregates. Then the specific suitability, there we're going to look at the suitability of the aggregates in concrete in a certain application or a certain exposure. And to establish that, in Belgium we have a standard that is being developed now for aggregates. For the binders, we already have a standard in which we can establish the same suitability for the alternative binders, but we are working currently on a standard to do the same thing for the aggregates. So there it will be a methodology described to establish, to show the suitability of the use of certain types of aggregates that are not allowed at the moment in the standard. So you can do this already, and certain plants already put on the market concrete with recycled aggregates. Of course, you can always go further, and at the BBRI we conduct since the 1980s research projects in which we are trying to push the boundaries of the application. When there was nothing allowed, we already made a building with recycled components and recycled concrete. We had a project, an idee-stortkabeton for the toekomst, for the future, in which we talked about, looked at the green concrete, and like Luc said, circular concrete is a project that ended recently at the end of 2020, in which we also looked at recycled aggregates, mixed aggregates, manufactured aggregates, alternative binders, and such, and there we conducted some research at lab scale, on a limited scale, but just to look at different innovative technologies. I'm going to discuss some of them very briefly. So we looked at maximum replacement. So the standard allows a certain replacement percentage of recycled concrete aggregates and also manufactured aggregates. And we made some, but we really pushed the boundaries. So we looked at 3 concrete compositions with recycled concrete aggregates, in which we replaced 90 to 100% of the natural aggregates by the recycled ones. And we looked also at the manufactured aggregates, mainly polluted sand that was cleaned, copper slag and inox slag. And these are only available in sand fractions, very fine fractions. So here we replaced mainly the sand fraction in the concrete. And we compared the results to a concrete composition with 100% of natural aggregates. So to be clear, this was a very limited scale research. We only made 1 concrete composition of each type. So we did not conduct a variability study or such things. It's really to look at what are the possibilities and what can we expect when we push the boundaries. We made 2 concrete qualities with these inert skeleton of the concrete. We made one of average quality, which is conform the requirements of the EN 206 for XC3, which has to see which means in fact a minimal cement content of 300 kilograms per cube and the water to cement ratio of 0.55. We used CEM 3A 42.5 to make the concrete, and then we looked at a high quality concrete with 340 kilograms and the water cement to cement ratio of 0.45. And we made concrete with that. Also, very important is that we added the recycled concrete aggregates in oven-dried state, and then we added extra water to take into account the water absorption of these aggregates, which meant in fact that high amounts needed to be added to take into account the water absorption of the recycled aggregates. Of course, the value we used to calculate this was the water absorption after 24 hours, and we know that when we mix dry aggregates in concrete, they will not absorb 100% of their water absorption after 24 hours. So there is added water that is not going to be absorbed by the aggregates. And of course, we looked at the influence on the mechanical properties, mainly the compressive strength of concrete. And we saw that in fact, when we look at the average quality concrete, the use of these aggregates in very high percentages did not lead to a high negative, important negative influence after 28 days. After 91 days, the influence became much more clear, but after 28 days, and this is still the time during which the evaluations are made, for the most part, there was no or very limited negative influence. Only when we looked at the high quality concretes, there the influence was immediately visible. and very significant. This is also the reason why the standard at the moment limits it at very small percentages. But you do not have to go to 100%, of course, of replacement always, but a higher percentage than what the standard says is certainly possible. And of course, there was also an influence on the durability properties. Mainly, we looked at the carbonation resistance, chloride, ingress resistance, frost resistance with the icing salts. And there we also saw a significant negative influence of the use of these aggregates, except for the frost resistance, because like we know, the frost resistance is mainly governed by the air content of the concrete, not so much by also, but more than the cement content or the water to cement ratio. So, and when we look, however, at the manufactured aggregates, there in the high replacements percentages that we used, 20 to 50% of these aggregates that replace the natural sand in the concrete, we could not see a lot of influence on the mechanical and durability properties, and we even saw on some aspects a better, a good influence of the usage of these aggregates. So this is a very important result of this limited scale investigation. We also looked at the smart crushing technology, in which we in fact a special equipment is used to break and to not only break, but it's a combination of different operations to get in fact the debris of the concrete to obtain the original components, so the original aggregates without any mortar still adhered, or very little mortar still attached to these aggregates, sand, and also a fine filler particle, which can then be used as in the cement production, or even as such in concrete production. So this is the theory. The environmental gains are, of course, that the influence, the negative influence on the concrete properties of the recycled concrete aggregates due to the attached mortar on the aggregates can be lessened, and so to push perhaps a low quality application of a certain batch of recycled aggregates to high quality application, just to improve the properties of these aggregates. So we did some experiments, and we went to Circulaire Mineral, which is a firm in the Netherlands, which has such installation to produce these kinds of aggregates. So what we did was we sent some debris, which we received from different producers in Belgium. You can see there are large, very large debris fractions that we sent to Circulaire Mineral, and they returned us a combination of all different fractions all together, and we then sieved them into the different fractions. And we can see that we did this for 4 different origins of recycled debris, concrete debris, and we saw that in fact all the returned samples, they showed a very similar aggregate size distribution of the aggregates, and also a lot of fines. What we did was in fact that we looked at the properties of the returned crushed recycled aggregates, and we saw in fact that the water absorption and also the micro de val, so the resistance to the mechanical resistance of these aggregates, they were very similar to normal crushed recycled aggregates. So in fact, the smart crushing technology that was used here with these aggregates, it did not added a lot of value concerning the properties of the crushed recycled aggregates. We also looked at the fines, you know, the powder fraction that we received. We looked at the reactivity as such, so without any treatment, without any heat treatment or such. We just used it like this in mortar, and we did not saw any contribution to the strength development of these fines. And we also looked at it under the different analysis, XRD, XRF, TGA analysis, and it all concluded that in fact, yeah, there is not a lot of reactivity, little to no reactivity left in those fines. So perhaps it has to do with the Belgian concrete. We use a lot of limestone, crushed limestone in our concrete in Belgium, whereas in the Netherlands a lot of rounded gravel is used in concrete. And I can see that the technology can be more effective on rounded particles than on angular particles. And we also have to look at the cost versus benefits. What about the streams, the high quality streams that are already available? Is this technology useful to heighten the quality of those streams, or is the gains that can be expected, are they in fact not, do they justify the higher costs of this treatment? So it seems a very interesting technology, but it has to be looked into if it's applicable on all types of recycled concrete. And thirdly, I want to talk about the carbonation of recycled aggregates. The recycled aggregates, they contain a large portion of mortar, and this mortar can be carbonated just like ordinary concrete. In ordinary concrete, it's not good that it carbonates because it's not good for the rebar that are inside the concrete. But in fact, the concrete itself, it gains in strength and it becomes less porous. And this is what we want to do with the active carbonation of recycled aggregates, so that the pores in the mortar portion attached to the original natural aggregates, that it becomes less porous. And you can see here, in fact, calcium carbonates will in fact fill up the voids inside the concrete, so that it becomes less porous and stronger and less susceptible to ingress of CO2 and water. So the gains here the environmental gains that can be expected is, yeah, that in fact the used recycled aggregates, they will not have they will have a lesser negative influence when we use them into concrete. The water absorption is lesser, so the water in the concrete can be managed more precisely. And perhaps we can push the low quality recycled aggregates that do not comply to the requirements from the standard. Perhaps we can push them with these treatments to the high quality standards of the standard. Of course, it would be ideal that we can use the CO2 that is produced in the cement production. If we can use this CO2 to carbonate these aggregates, so we can have an even higher environmental gain, but we are not there yet. At the moment, there is industrial CO2 that is used to produce this carbonation. So we did these experiments. We used an autoclave in which a very high percentage, 100% of CO2 was injected in the aggregates at high pressure, and we looked at the differences, and we could see that in fact it has a positive influence on the treatments. We looked at the water absorption and the particle density of the aggregates, and they showed improvements. But it was very limited. The highest positive influence could be seen in the sand fraction, and this is very normal. This is logical because the sand, in fact, consists of mainly mortar, and so it can be carbonated at a higher rate than the coarse aggregates. However, no clear influence could be seen on the mechanical properties of these aggregates, and perhaps this has to do with the intensity of the test method. And so the slide enhancement in porosity and the density, perhaps it doesn't have a very high influence on these properties. So it seems interesting, but again, we have to see at the practical application of this. How can we, in practice, begin to coordinate these aggregates? What about the CO2 capture to use the outputs of cement production in this application? And again, what are the gains versus the costs? Because there exist already high quality concrete aggregate streams in Belgium anyway. So perhaps this is not the miraculous solution to help this aspect. So this is what I wanted to say. I don't know if there are questions.
Thank you very much, Bram, for this nice presentation. I've learned that the standards are severe, but that with your project Circular Concrete, at least you made a step forward in pushing the boundaries. There are some questions, and the first one is from Tung Dao, our colleague from Lafarge-Volsen. Tung, you can ask your question.
Yes. Thank you, Rick. Hi, I'm Tung Dao from Lafarge-Volsen Research Center. So I have one question about the standard for the Belgian pavement design. Have you any idea about how they can take into account the recycled aggregate concrete in the concrete pavement design in terms of standard?
In what design?
In the pavement design.
In the pavement design, like I said, I'm no expert in pavement, but I think it's when I look at normal concrete, well, you can take into account. You can already do it. You can already use these aggregates, and I think in Belgium, in the standard Bestek 250, you can also in certain applications use already recycled aggregates. When I look at normally cast in place concrete, yeah, you can go higher, but you have to you have to establish a suitability, like I said, and this means in fact that you have to compare it to a concrete with ordinary aggregates and show that the loss in strength and the loss in durability aspect is not is similar to the ordinary concrete. So this is the methodology that is used. You can go a bit lower, but not too much, and this is the methods to show it for ordinary concrete.
Yes, so I can confirm that the substitution ratios are still rather limited, and let's say the same mechanical performance are asked, so there is no direct impact on the design of itself, but mostly it's now until now for low traffic applications.
Okay, got it. Thank you, and thank you.
Second question was for Mr. Vefa.
Yeah, hi, Muhammed Vefa Akpınar from Black Sea Technical University, Trabzon, Turkey. We did have experience using recycled aggregates from the municipal demolished buildings. We didn't have good luck in concrete, but rather we did have good high strength base layers. So I would rather use recycled aggregates in base or sub-base, in even some cases in the subgrades, but not in the concrete pavement layer. Yeah. So that would be a kind of an answer for Maringolo as well. My question was in terms of cost-wise, what is the ratio? Is it are they the same cost?
Yeah. Well, at the moment, it's more or less the same cost, because in Belgium anyway, I cannot speak for other countries, and in Belgium also, mainly in the Flanders part, there are some concrete plants that also produce themselves the aggregates. So for them, it's just the replacement of the aggregates in their own plant, and they have that way. They have a way to use their debris in concrete, and it's high quality debris. It comes from roads mainly, because roads is very uniform material. Other than, you know, like you said, the buildings, there are always other materials that are mixed, and so it's not easy to get high quality aggregates from buildings. But they use it in concrete, and they can deliver it at more or less the same cost. You cannot expect a lower cost because it still needs development, it needs research, and it's more or less the same as the natural aggregates. It also needs treatment. So at the moment, the cost, it's not like you in the, like clothing, recycled clothing is cheaper than new clothing, and that's not the case. So you don't have to assume that when you use or buy concrete with recycled aggregates, that the cost will be lower. And it's in fact often the otherwise. Often it's more expensive.
Okay, thank you very much.
So for the third question is for Mr. Koos Schenk.
You can see me now? Ah, yeah. Thank you for the presentation, Bram. I saw this presentation earlier and I saw that you mentioned again smart crusher again. I'm in front of the smart crusher that was shown by one of the drawings of my Octave, my patent. But I have nothing to do with this results. We are not invited to deliver material, so it's more a traditional crusher that comes also from Holland and have nothing to do with the smart crusher, and also the results are not comparable with each other. That was for the rest of the listeners. And
so Mr. Schenk, your statement is that you have an installation which would be able to give a better performance to the...
Yes, I'm certainly. So that's why the results came was less difference between the results because we didn't participate with this results.
Okay, that deserves further research.
Yeah.
Yeah, we work with Circular Mineral in this project, and I mentioned the smart crushing technology because that's the name of the technology. It's not I mentioned it not because it's a firm name. Also, it's I mentioned the technology, but
that's not a problem. We like to collaborate with you. But then take our materials, then you see a huge difference between a traditional crushed material, smart crusher materials.
I seem to remember that we were in contact in this project, but for some reason, we went with Circular Mineral for this part of the research. Yes, and our results weren't spectacular.
They are nice guys too, but that technology is completely different with our. So it is sheeps and apples in the comparison or something like that.
All right, so there is some further research to be done. And for the next question, we had first Mr. Talal Ashamari.
Yeah, hello. Do you hear me?
Yes, we hear you.
Yeah, hi, I'm Talal. I'm from University of Sheffield. Thank you for interesting presentation. I have a question about the density of recycled aggregate. As we know, the density is the main reason why the natural aggregate better than the recycled aggregate. is the smart pressure you have described before, is it defined the aggregate by density or not?
Well, as I said in my presentation, we could not see any improvement when we compare it to the normal crushed aggregates. But it's still the technology itself. Apart from the experiments that we did, the reason is the goal is to separate all the mortar from the original natural aggregates, so that in fact we get the original aggregates, we get the sand, and we get the filler, and the filler is then the cement. So this is the goal. In our experiments, it has not. It wasn't conducted very well, so we could not see any difference. But yeah, when you look at the original aggregates, of course the density will be much higher than the ones we looked at here. But yeah, the technology, as we looked at it in our research, did not conduct to higher densities. But yeah, perhaps co-skank with smart crusher. Perhaps when we do some experiments in the future, it will still work on Belgian concrete. I don't know.
Okay, thank you.
Yes. So the next question is for Mr. Wagner Maringolo from SEM Bureau.
Yeah. Just a moment. I did something wrong here. Can you pass me?
We hear you.
Yeah. I don't know if you are aware that the European Commission is planning to set up minimum recycled content in construction products. Do you have any view about this? If it's feasible in terms of supply, in terms of quality?
Yeah, that's always the question. I know that in the Netherlands they also have the Green Deal, and I know we're working on something similar in Belgium, in which we, I don't know if it is really obligate to work with a minimal percentage, but it is, in any case, it is in fact promote, give money or a reduction in costs to the firms that do it.
Yeah.
So we're working on something similar than as in the Netherlands. But at the moment it's not the case. But at the moment, and what we see now very often is that the contractors come to us because they saw in the Lastenboek and the
tendering documents.
Yeah, the tender that in fact they have to work as environmental friendly as possible, and they will be, and sometimes they are even rated and on this. So we see that more and more. So we're starting to see some very big changes in that.
I can confirm that indeed we see that mandatory legislation is coming towards us.
Yes.
I think then it's important to keep in mind the availability of the recycled aggregates, and obviously also the transport distances, in order also to keep it environmentally friendly, because otherwise circularity would be negative for CO2. So that's important.
That's very.
Okay. Thanks. Very interesting presentation. Thank you.
Yeah.
Thank you, Wagner. So next question is for Manu Diependalen. Manu, are you there? We do not hear you. No.
He lowered his hand.
So this means, I guess, that we have answered all of the questions. We have run a little bit over time. I'm just going to share one my presentation. So, ladies and gentlemen, I thank you for your presence, for your participation to this workshop. I believe we were about almost 90 participants at some moment, so thank you for that. Thank you for the interesting discussion also. I would say take a look at the website of EUPAVE, subscribe to our newsletter so you can stay tuned with all our latest news. Amongst which some upcoming events. We have in beginning of September a physical workshop by EUPAVE and FIBELCEM, the Belgian Cement Association, at the Construction Equipment Fair Matexpo in Belgium, Kortrijk. The theme is offset concrete paving, curbs, gutters, barriers, and so on. And also in October, that will probably be a hybrid event on pervious concrete pavements. So I want to thank our two speakers, Edwin Vermeulen, Bram, for their excellent presentations. Thank you all and hope to see you back soon. Take care. All the best. Bye.
Thank you. Bye-bye.
Bye-bye. Thanks for the presentation.
Bye.